and look at some, I would say, easier questions and ones that are more advanced. So as far as how you are going to use this video, an important question is, well, have you already worked on these problems authentically? Did you already try working on these best that you can with no notes, trying to work through to get the answers? If you did, I think that's going to give you useful feedback. If you haven't, well, then the feedback's going to be more limited because you don't really know where your current level of understanding is relative to these learning objectives. So in terms of authentic use, where do you stand? You're the only one that can judge that. Do you feel like you've already tried these questions authentically, or are you sort of fooling yourself? I'm going to add a couple different ways that you can use this video. The idea of self-explanation, and also what does it mean to learn from a worked example. There's this study that I find very persuasive. So within this one, it's a cognitive psych study. So what they did was they had students work on problems, learners work on problems in a certain way, and then see if by working on the problems, did it help them answer questions in the future. So one approach is they had the students with no self-explanation, meaning they just simply answered the questions and then tried to answer similar questions in the future. Retrospective self-explanation means after they finished answering a question, they would explain their process. And concurrent was as they were working on the problem, they were describing out loud what their problem-solving strategy was. When it came to specific concrete problems, meaning there was a really specific plan and it was clear what you would then do, subsequent performance was higher if the students had used this concurrent self-explanation the first time. If the question was more abstract, if the second question they were asked to do was not as clearly connected, man, look at this difference in performance. Absolutely huge. This is one of the most amazing findings I've ever seen in a study like this. And I think the reason why is if you're using this concurrent self-explanation, it gives you great metacognitive awareness. You can't BS yourself. You're going to know if what you're describing is actually a good plan or you just sort of hoping and you're putting down numbers and hope that it works out. So as you work through different examples, just pointing out, concurrent self-explanation, such a powerful tool. They've also done research on how students can learn from a worked example. So just looking at how a problem is done isn't really helping you generate your own understanding. So what you might ask from a worked example, questions like, well, what information is in the work solution that was not in the question? What did the problem solver have to recall? What formulas did they have to know? What equations? What definitions? Ask yourself, what information is in that work solution that was not in the question itself? You could also ask, how would the problem-solving strategy be the same or different if the question changes in some way? Look at what's in the question itself and ask if variables change, how would that keep the problem approach the same or different? Really good one, try to change the question and then answer it. This is what test writers do. This is what we do when we're trying to construct tests. We look at what we've been asking students to do in practice, and then we do a variation on that. Consider both minor and more substantive changes. Don't just say, oh, well, I'm going to change this value from 1 to a 2. Try to be more creative, and that makes it so that you're really stretching yourself. This idea of learning from a worked example, research has found you need to train yourself to do this. We don't naturally do this. We usually look at a worked example, nod our head, and say, yeah, that makes sense. To interrogate it and try to generate your own understanding, that's something you can train yourself to do. Something you might want to do during this video. So within this video, we're looking at ideas in chapter 4, and for me, they really begin by asking, what's in the beaker? We add something to the water. What does it do? We need that information that we're then going to connect to different types of reactions. So this first one of being able to make predictions for things being strong, weak, or non-electrolytes, really important initial skill. We also have to be able to use provided information involving solubility guidelines and provided information involving the activity series. For both of these, I think we want to know how we use the information and when does it show up? What kinds of questions are connected to these? So let's get started. So here I have 2 different questions that I think are related. So the first, which of the following is a weak electrolyte when added to water? So I would classify those. I see ammonium chloride, ammonia, nitric acid, and carbon monoxide. Ammonium chloride is an ionic compound. Ammonia, I'm recalling the information that it is a weak base. Nitric acid is a strong acid. And carbon monoxide, just a molecule. It's not an acid or a base. So I'm thinking that within this, a weak electrolyte would be ammonia. The ionic compounds, the strong acids, are both strong electrolytes. Carbon monoxide is a non-electrolyte. So now pause. What information is in the work solution that was not in the question? What did I need to be able to identify and know? How would the problem-solving strategy here be the same or different if the question were to change? And try to change it yourself. If you were to write another version of this, what would it look like? Here's one that I think is connected. I think the second one's more difficult, but I think it's connected. It's asking which of the following has the highest concentration of chloride ions. Do you see these as being connected questions? As I'm working through this, I see sodium chloride and calcium chloride. Those are both ionic compounds. They're both strong electrolytes. Carbon tetrachloride is molecular. Chlorine is molecular. They're both entirely nonmetals. They're not acids or bases. So I don't see either of these contributing chloride ions. Even though Cl is in the formula, they're not contributing chloride ions. So my analysis here, I see that I have 2 chlorides per formula unit for the calcium chloride. That would therefore double the concentration of chloride relative to the initial solution. So the calcium chloride has the highest value. These other two, yes, I see chlorine in the formula, but the molecules remain intact. There are no chloride ions present in those. Here are 2 related ones. We have formulas given, and it's asking which atom is reduced. To do that, we first need to assign oxidation numbers. So I show my assignment of the oxidation numbers. Remember, that's for every atom. I break down how I did the problem solving for the nitrate, because that showed up a couple times. Each of the oxygen is -2. The whole thing is -1. So that means that the nitrogen must be +5 in that polyatomic anion. Once I have those assignments, I can see that silver is going from +1 to 0. The silver is the atom that's being reduced. Key step within here is the initial assignment, and then also knowing that oxidation would be losing electrons and reduction would be gaining. This next one right here, absolutely the same plan, same procedure. These would be my assignments. I think if students are able to assign the oxidation numbers, then they can get the question right. But you got to be able to assign the oxidation numbers first. Take a second. Do you have questions on any of the assignments that I'm making here? When I then look at it, I see an example of nitrogen going from +5 to +2. That atom, the nitrogen in the HNO3, was being reduced. Both of these are related questions. I would classify these as saying these are connecting observations and these oxidation reduction reactions. Might help within the first couple here to say, well, what kind of chemical reactions taking place? So in this one, an example that's shown in the book would be magnesium. A strip of magnesium heated in a flame reacts with oxygen to form magnesium oxide. The book also has a similar example involving calcium. Hydrogen gas and oxygen gas, this explosion to form H2O. Both of those would be cases where if I assign the oxidation numbers, these are redox reactions. The next 2 examples are not. In chapter 4, there's quite a few different pictures where they're showing macroscopically the reactions that take place, and that's what this is related to. The second one right there, I'm going to go to the activity series for that. So we have a few different scenarios being described. If I have zinc solid being oxidized to form zinc 2+ ions, I also have to have something else being reduced. That's what's required if it's going to be in a redox reaction and the zinc is oxidized. So I think this idea of having the zinc solid oxidize and a solid begins to form, that would take place with the ions that I see below the zinc solid in the activity series. Nickel would be an example. If I added the zinc solid to a solution that included nickel 2 plus ions, the nickel would begin to coat the surface of the metal. Notice how hydrogen's also included right here. Hydrogen ions, all these other ones are metal, but the hydrogen's also listed. You could have hydrogen ions, H plus, in the solution, and those could be reduced, and those would form hydrogen gas that would then bubble out. Simply having the solid to dissolve, that seems inconclusive. That doesn't seem like an example of a redox reaction. I have to have one of these other phenomena also taking place for an observation. It's next two, also related to the activity series. This first one says specifically, based on the activity series. Within that one, based on the activity series, let's look at some data. So if I looked at some data, I find silver ions listed. And the question is, in which of these scenarios would the silver ions be reduced? Would they go from the right side back to form silver solid? These are the different ions that are in the beaker. When you added this, you'd have calcium cations. I see that when I add it with HCl, I would have H plus. I see platinum solid. I see nickel solid. Which of these is correct? Provide a self-explanation. How do you answer this? What's your process? The answer I see that works for me would be combining it with the nickel solid. With the nickel solid in my explanation there, I see nickel solid above the ions in my activity series. The nickel solid could be oxidized, and the silver ions would be reduced. This one is similar, but this is a more advanced question. There's a lot going on within this one. This is making connections to both of the different tables. There's examples where the choices describe a oxidation taking place. There's also examples where a precipitate form. There's also something where there'd be no reaction at all. So as far as precipitating form, if I have zinc ions, I could consider if hydroxide is present, those are low solubility, so I think that I could have a precipitate form. If I have my tin ions and I have chloride present, I could ask, well, would I have a precipitate form in that case? No, it doesn't look like it. It looks like the chloride would be soluble. But it's possible that I could have a tin hydroxide form. So that would be one that I think could happen. Similarly, could it be oxidized? Yeah, it could be oxidized, but it would have to be with something below it on the table here, an ion that would be below it on my activity series table. So how do I decide? Do I have an ion below it in the activity series? Do I have base present? Well, that's what this first part is involved. We're taking an acid and combining it with a base. They're both the same concentration, but I have more of the acid. So without even doing a calculation, I know that after I combine these two, it is an acidic solution. I've added more acid than base, so the overall solution would be acidic. So that makes this reaction here relevant. It makes it the case where the tin can be oxidized and the H plus can be reduced. If I had added together these same combinations, but I had more base present, then I think the hydroxide could have formed. This is a really comprehensive question, bringing together a lot of skills in Chapter 4. Almost all of them. Here we have a description of a neutralization reaction with an acid and a base, asking for the net ionic equation and spectator ions. Definitely want to begin by writing a balanced equation. I have the acid combining with the base. I'm forming the resulting salt and water. In the neutralization, look for that. Look for forming a salt and water. And I see that I have to have 2 of the acid for every 1 of the base, because I have 2 hydroxides for every 1 H plus. Start with a balanced equation. For seeking the net ionic equation, I'm going to break apart all of the aqueous strong electrolytes. Both of those conditions must be met. HCl is an aqueous strong electrolyte. Strong electrolyte because it's a strong acid. ionic compound that's aqueous, I'll break that apart. Water is molecular, I'll keep it together. Calcium chloride aqueous, aqueous ionic compound, I'll break it apart. The spectator ions that I see within here, I see the chloride and the calcium are the spectator ions. They're on both sides of the equation. If I were to cancel those off, I'm left with the net ionic equation. This one is similar, same strategy, but let's see where it takes us. So in this case, I say same strategy. I once again have an acid and a base provided. If I were to write the overall equation here, key thing, I'm going to break apart sodium hydroxide because it is an ionic aqueous compound, strong electrolyte. Same thing for the sodium fluoride. I'll keep the water together, and I'll keep the HF together. That's the key within this question, because HF, that's an important weak acid that we want to be looking out for. A weak acid is a weak electrolyte, not a strong electrolyte, so I keep it all written together. So I'm following the same plan that I just did a moment ago, but the key difference is I know that HF is a weak acid, not a strong acid. If I now look to see what I can cancel, I see a spectator ion of sodium on both sides of the equation. So my net ionic equation is what I'm left with. For me, this is exactly the same strategy I did a moment ago. I just followed it through. Really wasn't anything I had to memorize besides identifying HF here as a weak electrolyte. Here we see ones involving precipitate, so I'm thinking I'm going to need the solubility guidelines. So this first one right here, how many different compounds could form as precipitates when you combine these three solutions together? So I list all the cations and list all the anions. I see that silver hydroxide could form a precipitate. Poor solubility for that, it's not listed as an exception. Silver chloride, precipitate. Chlorides are usually soluble, but not with silver. If I look at any of the other combinations, I don't see calcium nitrate forming a precipitate. I don't see potassium nitrate. Calcium hydroxide was already a solution. I don't see the hydroxide forming a precipitate, so those would be the two. Within this one, same kind of thing where we're looking at the table, but we're using it more than one time. So in this one, we're seeking to selectively remove cations, where we'd form a precipitate and then remove that precipitate in stages. So it says the initial solution contains these cations. In the chemist, she follows this procedure. Let me step you through this one. So initially, if it contains these three cations, by adding sodium chloride, which of these would precipitate? I see that chlorides are usually soluble, but not if they include lead. So by combining the sodium chloride, I could form lead chloride and remove that from the beaker. If I have the barium and strontium left, by adding the sodium hydroxide, hydroxides are usually insoluble. As I look at this one, I don't like my answer, all right? I see that within here, both barium and strontium, it looks like here, both of these are listed as exceptions. I added a little prior knowledge I need to apologize for. I know information about the degree to which those are soluble, but you're not going to be expected to know that, okay? As I'm looking at this right now in my own self-explanation, I'm not loving this question anymore, okay? My strategy was that my approach then was finally you could remove the last one by adding the barium. As I'm looking at this one within my own self-explanation, I'm no longer loving the question. I think I needed to have different cations to make this question work. The idea of selectively removing them, it only works if you have it where for a given solution that you add, it reacts with one of the cations but not the other ones. And as I see this, I've learned something myself. I chose a poor set of ones within here. Sorry about that. Within this one, we have two examples involving dilutions. Here would be my first one. So if I'm doing a dilution, I'm thinking the equation M1V1 equals M2V2 is going to be useful. So I'm initially going to take the calcium chloride and see how does it dissociate. If I start out with a 0.1 molar solution, I get twice that for the chloride because it dissociates 2 to 1. I'm then going to use that solution in my M1V1 equation. I know what its initial concentration was. I know the volume that I'm transferring. I know the final volume, but I don't know the final concentration. That's what I'm solving for within this set. How about this one? Within our next one, how would you say the problem's approach here is similar or different if the question changes in this way? Read the second version closely. Would the strategy be sufficient, or do you need to modify it in some way? I think it's similar, but we just have to get to the initial starting point. And by that I mean, instead of having a concentration given, the mass was given. So I'm going to figure out how many moles I initially have, and from that I can convert that to how many moles of chloride I have in those 250 mils. With that information, I can determine what would be the concentration of chloride in the initial solution. At that point, I'm back to the same strategy of let's use our M1V1 expression. I know the concentration of chloride that I had present. This one's asking how much of the solution should I use if I want to have a given concentration and volume. So this would be the amount that I would be transferring over into that 500 mil volumetric. Very similar strategy, we just had a little bit more to do on the front end. Take a second with these two. These questions look very similar, but trust me, the first one is much, much easier. They look really similar in setup, but there's a real important distinction. See if you can spot it. For the first one right here, we have two different solutions that we're combining. So for both of them, we're interested in the amount of the bromide ions that are present in the solution. So if I have information involving the concentration and volume, I can combine that to get to the number of moles. Moles per liter times number of liters equals number of moles. So I can do that to figure out how many moles I initially have for the calcium bromide, and it dissociates 2 to 1. I could do the same thing for the potassium bromide and figure out how many moles of bromide that's given me into the beaker. Because the volumes are additive, I know that the total volume would be both of the volumes combined, and the total number of moles would be coming from both parts. So we just add together both features, and this is what describes the final solution. We have a total volume, total number of moles. We can now discuss its molarity. So for this one, we're really just combining two different strong electrolytes. They're both contributing the bromide ions. There's no reaction that takes place, and we're just describing the concentration of the new solution. This one right here, much more difficult because there's more going on. If I look at putting calcium bromide and silver nitrate in solution, I have a precipitate that will form. I have a reaction between the bromide and the silver. So now I have a lot more solution stoichiometry that I have to account for. I have a reaction of the calcium bromide with the silver nitrate to form this precipitate, the silver bromide. So I could figure out how many moles I have of both of the reactants, where I'm combining solution information and molarity to determine number of moles of each. If I track that down through a BCA table, I'm using up all of the silver nitrate. I'm using some of the calcium bromide, but I have some left over, and I have the product that forms. If I then look carefully as far as what I'm left with afterwards, I have some solid that's formed. Calcium bromide is giving me ions. Calcium nitrate is giving me ions because they're both strong electrolytes. And the one that I'm interested within here would be the concentration of the bromide. So within here, I could say it has 0.01075 moles of calcium bromide. When that dissociates, if I double it, that would be how much I have for the bromide ions. I see the volumes are additive, so I have the total volume. That would be the solution. This is a much more difficult problem because we're not simply combining two solutions. We have a chemical reaction that takes place. And for this one, I find it really important for my own understanding to keep track of it with a table approach like this. Here we have some neutralization reactions. Within these, crucial, we need to balance the equation to start with. Here would be my work through with that. I show a balanced equation involving sodium hydroxide and HCl. They react 1 to 1. I'm using a BCA table here just to keep track of what's going on. Not crucial. I combine the information about the solution, where I have volume and concentration, to figure out how many moles of HCl I have. Based on my change line with the coefficients, they react 1 to 1, so I figure out how many moles of sodium hydroxide I need. It's asking how many grams I would use of that, and so I'd be converting that using the molar mass to figure out how many grams I would need. If I'm looking within this one, and if I double back, it says how many grams of sodium hydroxide aqueous. That should probably say sodium hydroxide solid. I didn't mean that to be anything different. I'm looking for the grams of the solid there. The second one right here, balanced chemical equation. And we're asked, same kind of thing, how much would be needed to neutralize a particular acid? Crucial within the balanced chemical equation, I see 1 calcium hydroxide for every 2 HCl. If I use the solution information, I can see how much HCl I have in mole amounts. Within my change line, that will all be used up when it's neutralized. And I'll then see that I need half that many moles for the calcium hydroxide. I'm looking at the coefficients there. Since I now know how many moles of calcium hydroxide I have, let me put it into my expression, where I have molarity times a certain number of volume equals moles. Moles per liter times a certain number of liters equals moles. That's what I've solved for here. Crucial step within here, you need a balanced equation because the coefficients are not 1 to 1. It's really important to calculate the number of moles explicitly. Sometimes the students just have a lot of numbers and they never write that feature down, they get it wrong. Because we want to use the number of moles to then be able to convert, use number of moles and the concentration to figure out the missing volume. Thanks for watching the video. Okay, as I noticed it going through, I had 1 or 2 things I learned myself as far as the questions that I wrote. Hopefully you learned some things as well along the way. When I say let's move ahead, reach out to me if there's ideas and topics in here that you still find confusing, and we can work together to improve them as we move